Hello, welcome to the channel. My name is Qiujiang Lu, the author of this paper, Constructing 3 and higher n-dimensional complex number spherical and Cartesian coordinate systems based on rotation factors. In the previous video, we have explored the fundamentals of the imaginary unit and the complex numbers in a two-dimensional plane. We live in a three-dimensional space. In this video, we are going to focus on investigating into 3D complex number system. It's hoped that in the process, we may gain more appreciation about the wonder and the beauty of math and nature. First, let's briefly review the concepts and understandings from the previous video for 2D. We will then extend the concepts to 3D about the existence of a rotation factor set. It's found that there exists a rotation factor set E. Complex numbers may be considered as position numbers. Each member in position number set P is constructed by a member in real number set R and a member in rotation factor set E. 2D vector rotation. In a two-dimensional plane, vector P can be rotated by a rotation factor of an arbitrary angle theta. E to the power I theta is the rotation factor. The rotation angle theta is relative to the vector P. Based on rotation factors, two-dimensional polar and Cartesian coordinate systems have been constructed. Here, we will extend the similar construction concept to three-dimensional space. Constructing three-dimensional coordinate system axes. RE is a real number axis. O is the origin. ORI is an axis that's orthogonal to the RE axis. ORJ is an axis that's perpendicular to the plane formed by the RE axis and the ORI axis. Real number 1 is considered as a unit vector pointing to the positive RE axis direction. Applying orthogonal rotation factor I to unit vector 1 makes the vector rotate to unit vector I, which points to the positive ORI axis direction. J is another orthogonal rotation factor. Applying the orthogonal rotation factor J to unit vector 1 makes the vector rotate to unit vector J, which points to the positive ORJ axis direction. Here, 1, I, and J can be considered as unit vectors for the respective axes and have been explicitly denoted by arrows. In reality, their directions are implied without being denoted by arrows, but in our mind, we can still consider them as unit vectors. On the other hand, I and J are also orthogonal rotation factors that make the unit vector interact and interchange to each other. For example, unit vector I can be rotated back to unit vector 1 by multiplying minus I. Unlike conventional unit vectors, I and J are also rotation factors and can participate in algebra operations. After setting up the 3D axes, we may then proceed to construct a spherical coordinate system. P sub 2r is a position number representing a point in the second dimensional plane that's formed by the RE axis and the ORI axis. Theta is the angle between the position number P sub 2R and the RE axis. R is a real number in the RE axis. I-associated rotation factor e to the power I theta can be used to rotate the number r and make the number rotate to p sub 2r. That is, we have this result: p sub 2r equals r e to the power I theta. J is for the ORJ axis for the third dimension. J associated rotation factor e to the power j phi can be used to rotate the point P sub 2r and make it rotate to the point represented by position number P. Thus, we have this result: P equals P sub 2r e to the power j phi. Combining these two, we obtain this final result for the position number in 3D spherical coordinates. P is position number, which is equivalent to 3D complex number. R is the magnitude of the position number. E to the power I theta is the rotation factor for the second dimensional plane. E to the power j phi is the rotation factor for the third dimension in the j direction, which is the ORJ axis direction. So, we have obtained the formula of 3D complex numbers in spherical coordinates. From this formula, we can see the result is succinct and elegant. For two-dimensional plane, angle phi is 0, and this factor e to the power j phi is 1. The formula becomes 2D complex numbers in polar coordinates. Compare with a two-dimensional plane. For a three-dimensional space, a third dimension is introduced in the j direction, and a rotation factor associated with the j direction appears in the formula. Next, we will obtain the transformation from spherical to Cartesian coordinates. Here sub 2 means parameters in the second dimension or 2D plane. The point represented by position number P sub 2 is a point in the 2D plane. The point represented by position number P is in the third dimension, and its corresponding projection in the 2D plane is P sub 2. P has a magnitude r, and P sub 2 has a magnitude r sub 2. It can be seen that r cosine phi is r sub 2. R sub 2 cosine theta is A. That is, we have this result for A. Similarly, r sub 2 sine theta is B, and we have this result for B. Further, r sine phi is this length, which is the projection C in the j direction. Thus, we have this result for C. This is the expression for position number in 3D Cartesian coordinates. Inserting the A, B, C results into the expression, we obtain this formula. This is the transformation formula from spherical to Cartesian coordinates. Likewise, from the geometry, we can obtain the transformation from Cartesian to spherical coordinates. Magnitude r is the distance between point P and the origin. R sub 2 sine theta is A. So we have this angle theta. This square root equals R sub 2. R sine phi is C. And we have this for angle phi. With this transformation, we can obtain r theta phi from Cartesian coordinates A, B, C. Next, about multiplication commutative property of rotation factors. We will illustrate that rotation factors are commutative in the spherical coordinate system. In this figure, multiplying r with I associated rotation factor e to the power I theta makes the point rotate to P sub 2r. Further, multiplying with j associated rotation factor e to the power I phi makes P sub 2r rotate to P. So P equals r I associated rotation factor multiplied by j associated rotation factor. On the other hand, multiplying r with j associated rotation factor e to the power j phi makes the point rotate to P sub 3r, and multiplying with I associated rotation factor e to the power I theta makes P sub 3r rotate to P. Thus, P also equals r j associated rotation factor multiplied by I associated rotation factor. We can see that changing the multiplication order of the rotation factors will not affect the result. That is, the rotation factors are multiplication commutative. Next, about the interaction between orthogonal rotation factors I and j. As mentioned before, I and j can be considered as unit vectors. On the other hand, there are orthogonal rotation factors that can rotate vectors. To specify the rotation target, here we define that the former is rotated by the latter. For example, ij means that I is rotated by j. It should be noted that we can also define the other way around. It will not change the result. For ij, I is considered as a unit vector pointing to the positive ORI axis direction. I is rotated by orthogonal rotation factor j with the resultant unit vector pointing to the j direction or the positive ORJ axis direction. That is, ij equals j. For ji, j is considered as a unit vector pointing to the ORJ axis direction. J is rotated by orthogonal rotation factor I, but the rotation generated by I is in this direction, parallel to the RE-ORI plane, and therefore cannot make J rotate. In other words, J remains the same. Thus, Ji equals J. We have this identity. In fact, more generically, for an arbitrary angle theta, any point in this line on the plane is also rotated to the ORJ axis by rotation factor J. That is e to the power I theta multiplied by J equals J. Also, rotation factor e to the power I theta makes the vector rotate in direction parallel to the REORI plane and cannot rotate J. Thus, e to the power I theta also equals J. We have just obtained the interaction results by geometry and the rotation factor concept. In fact, the same results can also be obtained by the transformation formula. In spherical coordinate system, rotation factors are commutative. For position number e to the power I theta, J equals this. The magnitude of the position number is 1 and the angle phi is half pi. In the transformation formula, cosine half pi is 0 and these two terms are 0. Sine half pi is 1. The resultant P is J. That is, we have this identity. This identity for Ij is the special case of the above identity. Previously, we obtained the spherical to Cartesian transformation by geometry. Next, we will show that the transformation can also be obtained by rotation factor multiplication algebra. This is the formula for position number in spherical coordinates. Using Euler's formula for J associated rotation factor, we have this result. Multiplying the I associated rotation factor to these two terms, we have this equation. In this equation, from the previous discussion, we note that the I associated rotation factor multiplied by J equals J. This term becomes this. With Euler's formula for this rotation factor e to the power I theta, this term becomes these two terms. This is the transformation formula, which is the same as the one we previously obtained by geometry. Next, we will discuss the multiplication of position numbers in spherical coordinate system. P sub 1 and P sub 2 are two position numbers in spherical coordinates. Since rotation factors are commutative, the two position numbers are also commutative. Here is the multiplication result for the two position numbers. The result is a new position number in spherical coordinates. Using the previously obtained transformation formula, the multiplication result can be transformed back to the Cartesian coordinates. The result is this formula. Next, about multiplication of position numbers in Cartesian coordinate systems in other dimensions besides 3D. According to Frobenius' theorem, for division algebra over the real numbers to be finite dimensional and associative. There are only three such division algebras: real numbers 1D, complex numbers 2D, and quaternions 4D. R and C are commutative, but H is not. There is no division algebra in the 3D Cartesian coordinate system. Now, back to 3D, about the multiplication of position numbers in Cartesian coordinates. Here, P sub 1 and P sub 2 are two position numbers in 3D Cartesian coordinates. Since there's no division algebra in 3D, performing the multiplication of the two position numbers in Cartesian coordinate system is not feasible. On the other hand, in reality, the multiplication of the two position numbers represents a vector rotation by another position number, and obtaining the correct multiplication result is meaningful for practical applications, so we may take an alternative approach via the spherical system instead. First, transform the two position numbers into spherical coordinates. Then, perform multiplication in spherical system and transform the multiplication result back to Cartesian coordinates. In reality, this multiplication step is for thought process and is skipped. We may directly use this transformation formula. This is the formula for 3D vector rotation. Vector P may be rotated by two rotation factors in 3D. The resultant vector is P prime. It should be noted that the rotation angles theta and phi are relative to the vector P. Vector rotation may find its applications in physics, chemistry, such as describing molecular structures, and other fields. In the end, let's summarize the key points. A spherical coordinate system for 3D complex numbers has been finally developed. Before, we do not have a spherical coordinate system for 3D complex numbers. Now, based on rotation factor concept, the 3D spherical system has been obtained, and the result is succinct and elegant, indicating that the rotation factors is the native language for the spherical system. Multiplication of 3D complex numbers in the spherical coordinate system is commutative. Actually, the rotation factor concept can also be further extended to higher n-dimensional spaces. This may be discussed in a separate video. Thanks for watching.